The homework will be out tonight. The auto grader might be due a little bit after that. There's a chance the auto grader will be due a little bit after because we do have to have some work to get some of the deep learning libraries working on AutoLab. But the assignment should be up. There are actually going to be 4 problems on the assignment. Ideally, again, assuming we're able to get the auto grading working. But the 388 version will do 1 out of 3, and then the 688 version will do 2 out of 3. With the possibility of getting some extra credit. So, if you already have full marks, you can't get any more. But for those that had some problem, they actually can get extra credit by doing 1 more assignment for each level. But there are actually more problems than you'll need to do, certainly. And that'll be discussed when the TAs release the homework tonight. Lastly, I will have to run right after class today, so I can't stay to answer questions. I'll have to actually just run off. But I will hold an office hours this week, the high-level one. I think that I'm guessing the ones that are held when the homework's just been released, and it's also Carnival on Friday, so I'm guessing it'll be pretty sparse. I might just I might not even record it. I might just have a time where you can come also ask questions. But if you have any questions you want to ask me now after class, just try to ask me on Friday instead. Okay. Oh, and the last thing I'll say is these are now all very partial, though I haven't been uploading them, but I have sort of partial notes for a lot of these things written. For the problems that are on this homework, I will post the notes, say, by Friday. I need a little bit more time to finish all of them, but it'll be in a big bunch. But I'll post those notes by about Friday for this set of homeworks. Okay, so let's get started with this lecture today. It's going to be about probabilistic modeling. So we covered kind of basic probability. But this lecture also is a little different take. It's, what do you do when you have a bunch of data and want to model it in a probabilistic manner? And we're going to cover a few topics here. So we're going to cover first a general definition of what are called probabilistic graphical models. Then I'll talk about probabilistic inference. And I'll talk about then Bayesian. And finally, I'll talk about probabilistic programming, which are kind of tools, programming tools for how you actually do a lot of these things in practice. This is going to be a very, very quick overview. I mean, there's entire courses on just probabilistic graphical models that cover, all these things. But this is the subject of an entire course here at CMU. So this is going to be a very, very high level. And what I want to convey more than anything else is not the details. The details, especially if you've never seen this before, they are going to be a little bit tricky for this lecture. But I want to convey some of the basic ideas of probabilistic modeling and how you use programming tools to actually solve or build these probabilistic models over data. So let me start off with probabilistic graphical models. At their core, what these probabilistic models are, they're about ways to represent high-dimensional distributions. So a way to model distributions P of x, where x here could be some very large set of random variables. And the problem, of course, with this is that if we tried, even if x was discrete, right, and it can be continuous in a lot of cases that we care about, but even if it's discrete, as the dimensionality of this number of objects you want to model increases, right, as the size of the vector x increases, it becomes harder and harder to represent this distribution analytically, right? So you have to do things like, we saw the example already of naive Bayes, right, where you would need, if you didn't have an independence assumption, you need a lot more parameters to represent your distribution. And in general, even if you suppose these things are binary valued, then to represent a full joint distribution over n variables would require 2 to the n different probabilities, right? You have to model the probability of every possible combination that these things could take on. Now, what graphical models do at their foundational level, and this is actually going to be true of all the models we're going to talk about here so far, is that they offer a way to represent these same distributions more compactly. And they do so essentially by exploiting the conditional independencies of these distributions. They're also, I'll actually mainly highlight here in this lecture, they're also a very nice way of kind of telling stories. I mean, they're not how the data really comes about, but they're kind of telling stories about processes that approximate how our data is generated. Okay, so these things actually go hand in hand. The notion of sort of these what are called generative models and these conditional independencies, but we'll see that a lot more later. And the last thing I'll say is for this lecture, the only type of graphical model I'm going to talk about is what's called a Bayesian network. Though even with that, I'm not going to focus too much on the details of Bayesian networks. I'm going to instead focus on sort of the more kind of empirical and practical side of things about how these actually work in practice. But I'm going to use the word probabilistic graphical model and Bayesian network interchangeably, even though there actually are differences. There's much broader classes of probabilistic graphical models that are not Bayesian networks. Okay, so let's jump into, though, defining what some of these graphical models really are foundationally. So a Bayesian network is defined by two things. I actually won't write it down here because this is sort of the technical definition, but we're going to quickly move away from this in terms of how we think about these things. So it's defined by a directed acyclic graph. And the nodes in this graph correspond to random variables in our distribution. All right, so we're going to define a graph over the different variables in our distribution. The vertices here are x1 through xn. Those are our random variables. And there are some edges. And it also contains a set of conditional distributions which specify one of the variables given the parents of that variable. Okay? The parents here meaning the parents in the graph structure. So it's a directed graph. So the parents of a node are just the nodes that have an edge pointing to that node. It is an acyclic graph, so you cannot have loops in this graph. It is always directional. And it defines the joint probability distribution in the following way. So we define the probability of x is the product of the probabilities of each of these conditional distributions. So the probability of xi given some other ones. Now, we're going to see some examples of this in a second that will hopefully make this much more concrete. But this is kind of the formal technical definition. Now, I should say this is actually equivalent to specifying a very particular set of conditional independence assumptions over the different random variables. Though in general, actually, we're not going to focus on this element today. We're not going to focus on the independence side of things. We're going to focus mainly on just sort of the structure and the definition of these models in terms of probability tables, essentially, or conditional distributions. So let me offer a really quick example here. So just to show some sort of very simple example, here would be a distribution over 4 variables, right? x1 through x4. And suppose these are even binary variables. Okay, so these are 4 sort of coin flips where the second coin depends on the first coin, the third coin depends on the second coin, etc. Okay, and so what a Bayesian network over these 4 variables says is that I can write the joint distribution, that is the distribution over all my variables. And again, I'm using capital letters here. That means that I'm talking about the distribution over the factor over all those 4 over all possible values of all those 4 variables. But the key idea here is this distribution here can be written in factored form in this manner. So normally you couldn't do this, right? Normally you could not represent the distribution like this. But what the Bayesian network probability assumption says is that actually the distribution is the product of all the variables given their parents in the network. And so this is x1 given nothing because there's no parents of x1, x2 given x1, x3 given x2, and x4 given x3. All right, so it's going to be the product of these 4 different distributions. Now, the advantage here is that, of many advantages here, is that we need much fewer parameters to specify the thing on the right than the thing on the left in general, right? Because if these things are binary, we would need 2 to the 4 different parameters. I guess 2 to the 4 minus 1 because they have to add to 1, so you can leave off the last one if you want. Different parameters to specify this whole joint distribution over all the variables. Right, I would need to specify kind of, what's the probability of 0, 0, 0, 0, 0, 0, 0, 1, etc. Okay? But with this factored representation of my distribution, I actually can do this in much fewer. So I need really 1 parameter to represent the p of x1, right? Because it's just the probability of being true. The false being false is the opposite of that, 1 minus that. And then for each of these, I need 2 parameters to represent each of these things, right? Because I have to represent the probability that x2 equals 1, say, given both possible values of x2. And the probability that x2 equals 0 is just 1 minus that. So in total then, I would need 7 parameters to represent this whole thing, whereas I would need 16 to represent the thing on the left in general. And of course, this would keep going, right? So in general, if I had n variables here, I would need 2 to the n, whereas here I would need 2 times n parameters to represent this sort of this Bayesian network. Okay, so that's all well and good, but what I actually want to emphasize is not just this sort of factored probabilistic form of the distributions. What I actually want to emphasize in this class today is what's called the generative model of this network. Okay, so this is actually going to be the more important aspect here. So the way you should think, at least at a high level, and I know there actually are some problems with this, especially the fact these are not necessarily causal models in the broad sense. Of them as kind of causal models here. The way you should think about Bayesian networks, or in general probabilistic graphical models are really, or a certain class of them at least, are really as what are called generative models. So what generative models are is they present a way of constructing the distribution sort of step by step, okay, and particularly samples from the distribution kind of a step-by-step fashion. So what I really want to emphasize here is kind of the story by which this data is generated. Okay, so the story that this data gets generated goes something like this. X1 is a Bernoulli random variable. That means it's a binary random variable, right? They can take on 2 values, and it does some parameter there, which I'll call phi1. Okay, that's just a number between 0 and 1. Okay, and the way this data is generated is that I first sample x1 for Bernoulli distribution. All right, that gives me a value for x1. So maybe I'll even write this. Oops. Oh. All right, so step 1, I sample x1 from a Bernoulli distribution. I'm going to say that has parameter phi1 there. Okay, so at this point now, x1 is either equal to 0 or 1. And that's my value that I assigned for my first variable. Next, I'm going to sample x2 from a Bernoulli distribution with parameter here phi2 subscript x1. What this means is we actually have 2 different Bernoulli distributions here, one parameterized by phi2 0 and one parameterized by phi2 1. And depending on the value of x1, I either will pick the first one or the second one. Okay? So essentially, the value that x1 takes on will impact the next distribution I sample from. Okay? And I repeat this process, right? Then I sample x3 from a Bernoulli distribution with this parameter, then x4, etc. Okay? And the important part here is the way to think about this is kind of as a sequential process for generating my data. All right? And this is really the key aspect of a generative model, is that it gives us a way of generating samples from our distribution. Okay? And oftentimes samples in this way are easier to think about than the entire joint distribution, right? Because they're just actual instantiations of numbers. They are, x1 has a value at 0, 1, x2 has a value, etc. But the important part is that these things can be very correlated, right? So, it could be the case that x2 is always equal to x1 or always very close to equal to x1, right? Because maybe, maybe phi 0 of 2 is like, this would be the probability that it's 1 given it being 0. It could be something like 0.01, whereas this thing could be maybe 0.99. So in this case, if you had these 2 values, x2 would often be the same value as x1. Right? But what it does is this gives us a way of, despite the existence of all these correlations, it gives us a way of generating samples from this distribution. Right? That's really what a generative model is. It's just a recipe for generating samples from some distribution. And this is a very, very powerful paradigm. And in fact, we've actually already seen a lot of examples of this already in class. So for instance, both naive Bayes and the mixture of Gaussians are examples of generative models. Okay, so the example of naive Bayes, and then 3, he had this 4, etc. Okay, so let's think about some examples of these. All right, so naive Bayes we saw before. And you remember the story of naive Bayes was that the features, all the features of random variables, x1 through xn are random variables, and the key assumption of naive Bayes was that the features are conditionally independent given the class label. So the way to think about this as kind of a generative model story is to think of it as the following. I first sample, again, this is going to be a way for me to generate my samples from the underlying naive Bayes model. This is not, so forget about fitting the data right now. Assume we have parameters for all the naive Bayes distributions. This is just about how I sample from my model given that. So in particular, the way the story of naive Bayes is that I first sample y from Bernoulli, say. There also are categorical versions of this. Bernoulli with parameter phi. Okay, so that's, I first, flip a coin. If it's heads, I have a positive class. If it's tails, I have a negative class. And then I sample xi given y equals, the little value of y that it's been, is going to be sampled from, say, a categorical distribution. It could also be binary here, but, if you have categorical variables and a binary label, it would be categorical here. With parameter, I don't know how to write this out, right? Phi I subscript y. Okay, so what this means is that, depending on what my class is, I'd pick a different set of parameters that govern this distribution. But for a given class, this parameter governs the distribution for the ith feature, and then this would be all, of course, for all my features for I equals 1 to m. So that is the story of naive Bayes. Now, what's very important, and this is sort of a key point that's going to come next, is that nowhere when we run naive Bayes, typically, do we actually generate data in this fashion, right? Once we've fit our naive Bayes model, we don't then say, okay, well, let's now generate some more examples. Let me flip a coin to select the class, then flip more coins to select what my features are. That's not really how the models are used in practice, but it's important to understand this model as this sort of story as a probabilistic model. Because what we're going to do eventually then is we're going to say, okay, this is my story of how data is generated, but I'm going to assume that I actually observe some of my data. So I'm going to assume that, even though data is generated in this fashion, given that, I'm going to observe some of it with where I know the x values. I want to predict what the y value is. This is going to be what's called inference, and we'll talk about it in a second. But the key point here is that even though we don't ever run this sort of sampling procedure as is in naive Bayes, this is still the process, the distribution that governs this algorithm. Right? That's sort of the important way to think about these probabilistic models from a modeling perspective. Another one that we've already seen, a very similar model actually, was the Gaussian mixture model. This is what we did, what we used for our example with EM, for density modeling with a mixture of Gaussians. And in this case, Z, this is our hidden variable, right, was generated from a categorical distribution with parameter phi. All these phis, I should say, are different here, of course, right? This is the phi for the naive Bayes Bernoulli. This is a phi for a categorical distribution for Gaussian mixture models. And then, given this hidden cluster ID, you can think of it as our variable x, given z equals little z, is sampled with some mean mu z and covariance sigma z. Right? So again, we don't actually generate data this way usually. What we do is we assume we have some observed data x, right? And then we fit a model like this to the data. But this again is the generative process that governs our. If we were to generate samples from this, the way we would generate samples is we first sample what that hidden variable is, z, and then given z, we would sample the actual mean, the value x from a Gaussian distribution with a certain mean and covariance specified by the value of z. And in fact, this can get very sort of fancy very quickly. So another thing that we sort of didn't really emphasize too much, but which I mentioned briefly, is that linear regression. This is what in our probabilistic model, or sorry, in our probability lecture, I mentioned, or just no, the maximum likelihood estimation lecture. I mentioned that linear regression actually could be phrased as a probabilistic model as well. The assumption there is that the output y is just that the output y given x is normally distributed with mean theta times x, theta transpose x, theta are our parameters, and some variance sigma squared. Okay, that was, importantly, we didn't give any sort of distribution over the x's themselves here, but we just gave a linear, least squares is really about a conditional distribution of the outputs given the input. And you can get now very fancy. So I'll just sort of mention two more. I'll mention this one because we're going to talk about it a little bit more later, when we for at least it's a more complex model when we talk about Bayesian modeling. But this is the change point model. So the idea here is that you have some parameter t that governs this distribution, and also parameters mu1 and mu2 and sigma. But what you do here is I sample x here uniformly between 0 and 1. So here's 0, here's 1. So I first sample x uniformly on this line here. And then there's some threshold t here, where if x is lower than that, I sample the y, the other coordinate, I'll call this a coordinate y here. I sample y from a Gaussian with some mean, and if it's bigger than the threshold, I sample with it from another mean. So one sort of way to look at this data is it could generate data that looks like this, right? So say I have samples here that in this space it all kind of lies in this range here. So this is Gaussian with some mean around here, say. And then if I'm above this, though, I have a Gaussian that looks more like this. So I have samples that look like this. So this is mu2. All right, so this would be one set of data you could generate from this model, right? Where the parameters of this model, of course, are the two means, the variance, and this threshold t. These types of models are very useful because when you have like temporal data that all of a sudden changes its distribution at some point, so you have some event that happens and the data changes, these kinds of change point models can be very good. So detecting like when this change happened, for example, estimating what t should be is a very important part of a lot of data modeling, or certain types of data modeling. And lastly, I'm not going to get into this at all, but I just want to sort of emphasize that these things can get quite involved pretty quickly. You have, and this is actually even not that complicated a model. You have models that they're sort of are very powerful. So one of the more classically known, or I guess at this point it's classic, it's only like 15 years old, but one of the more popular ways of modeling topics and documents is a model called latent to reach allocation. And this actually itself is also a graphical model. So I won't get into it. Basically, you sample things like topic distributions, word distributions for each topic. And then for a given document, you sample a distribution over different topics that this document sort of contains. And then for each word in that document, you would sample from the bag of words for that, basically for those topics that the document is contained of and for the words of that topic. So this gets quite confusing here. And the other thing I would say is, as with all these things, it is not as if our data we ever will observe really fits these models, right? Again, the story here for generating these models kind of is something like, I grab into a big bag of words and pull out a bunch of words corresponding to different topics, and that's how I assemble a document. And real documents are not written that way, but this is how the models work, right? So the important part of all of these things is that these models, probabilistic models, can work very well at extracting the relevant quantities from data, even if the data is not really generated by that process. Right? So it's generated by something that looks kind of like it, but is actually quite different. This is not, don't worry if this is not understandable. I haven't even defined what regional distributions are and stuff like this, but it's just a bunch of different distributions. Okay, so what this hopefully sort of gives you some sense of is kind of the type of distribution that we can express using these generative model frameworks. What I want to highlight next is the basic problem of what's called inference. So inference is the problem of if I observe some of the variables, the value that some of the variables in my graphical model take on, how does this change my distribution, or how, what does my distribution look like over the remaining variables? All right. So I forget if I have the example of this. I think I do in a second. But this is in the case, for example, of naive Bayes. The inference problem here involved the following. It involved the question of, given some features for an example, what's the distribution over possible classes? What that would look like is, my naive Bayes model was I had my first choose my class, then given this class, I choose, x1, x2, xn, right? And I choose these all independently given the class. And the inference problem is, if I now observe all these things, how does this inform my distribution over y? Can I, for example, in the case of naive Bayes, compute exactly what the probability of y is given 1, y equals 1, and the probability of y equals 2, given these observations. Now, the point I want to make sort of on this slide here is that depending on the structure of your network, this can be an easier or a harder problem. All right, so if I have this sort of chain Bayesian network, you can think of it like a chain generative model. So I first generate x1, then I sample x1 given or x2 given x1, then x3 given x2, etc. So it turns out that if I actually know the value of x1, this is actually a pretty easy thing to sample from, right? Because or even express exactly this distribution, because I already know how to sample x2 given x1, then I just sample x3 given x2, etc. So if I want to create a generative model for this distribution where x1 is known, it's actually quite easy to do, right? I just sort of say, okay, I just fix this to be its value and continue with the rest of my generative model. But the point that I actually want to make here, and I should say this notation means that the things that are grayed in there are the variables that are observed, and the things that are white are the variables that are unobserved, the things that we want to estimate the distribution over. But one thing you can hopefully try to convince yourself of is that depending on which variable you observe, this can be easier or harder. So so this is a kind of an easy one, right? If I know the value of x1, I can kind of easily choose the value. I can easily come up with a distribution over the values of the remaining elements here. On the other hand, though, if I just know x4, so someone tells me this is my generative process. Here's how I generate my data. And by the way, you've observed that x4 takes on the value 0. Okay, now the question is, what is the distribution over the remaining x1, x2, x3? And in fact, this is exactly the case that we have in naive Bayes here. In naive Bayes, you're not of the case, it's not usually the case where someone tells you, I have a class, my class there is 0, what's the distribution over samples? No, you're told what what's the distribution over features. No, you're told what the different feature values are. And I want to estimate, what's the probability over the classes here. That's actually the fundamental problem, the fundamental kind of inference problem of naive Bayes. So the problem here is that now there's nothing kind of formulaic to do. I mean, in the case of naive Bayes, you can use Bayes rule. Actually, everything here does boil down to Bayes rules at some point, but it can get quite cumbersome. And it turns out that in general, there's no way to sort of generally represent these things compactly. You can actually have situations where, even though the distribution is sort of nice like this, not in this exact case, but similar cases, if I observe one variable, I have no choice but to represent sort of the full joint distribution over all my unobserved variables if I want to do exact inference. So because of this, there are really 3 key approaches to how inference is done. Actually, before I keep going, though, I want to stop and pause to ask questions. Does anyone have any questions And actually, realizing I'm very aware this is going quite quickly. This is, again, one of these kind of one-off lectures that is sort of self-contained. But if you have questions, please do stop to ask. Okay. When do you use probabilistic models? So, I mean, we've already seen how naive Bayes is useful, right? Anytime you want to quantify the distribution over some set of objects, it can be very useful to do probabilistic modeling, right? Because unlike more, I wouldn't call them, I mean, let's see. So there are many times, I mean, the core question of data science to a certain extent, right, is we observe some data and we want to know what this says about the rest of the world, right? And so one key thing you can do to explain this is you define a model of what the world looks like, how this data is generated, which could be very approximate, as we've seen, right? It does not have to be that good of a model. And then we infer from what we've observed what the remaining state is. Okay? So that's sort of the idea, and that's really kind of hugely applicable to a lot of scenarios. We'll talk about it in a second, and actually in the homework we'll go over one. But the basic idea is that this is a little bit more, what these techniques do is they do a little bit, they kind of look under the hood a little bit more than a lot of the machine learning techniques. So a lot of machine learning techniques we use is sort of take input and you just predict some output, right? And that works great if you have known input-output pairs. But when you don't really observe everything in the world, when you have like an unsupervised problem like you do with mixture of Gaussians, it can be very beneficial to sort of hypothesize a probabilistic model for how the data is generated, and then figure out if that model is true, what are the hidden parameters that govern my distribution. That's the basic idea. So given that, of course, it's important to know, how do we accomplish this inference task? In other words, given the fact that I observe some of my data, how do I infer something, be it the full distribution or just things like can I draw samples from, the remaining variables in my generative model? Okay, so given, let's see, examples here. Given features in naive Bayes, feature values, observed feature values, how can I infer what the class label is? In a mixture of Gaussians, given just an observation of the data, a new data point, how can I infer what the different cluster probabilities are for that data point? For change point modeling, if I'm just given, an X and a Y pair, how can I determine the probability of this pair occurring? Things like this, right? So this is all, or more generally, given a lot of X and Y pairs, maybe how can I estimate, where the change point in the data is? Okay, so these are all, that last one's a little bit more of a parameter estimation task. I'll talk about more later. But these are all questions that sort of can be answered through these probabilistic kind of inference methods. In the last case about where the change point is, it's a slightly different model, but we'll get to that in a second. Okay, so there are really three types of things you can do when you want to understand the distribution of the unobserved variables in a probabilistic model given the observed variables. On the first thing you can do is what's called exact inference. This is actually what we did with naive Bayes. We computed exactly, under our assumptions, that this independence assumption, exactly what's the probability that y equals 1 and what's the probability that y equals 0. Okay? And there was nothing approximate about that. It was, the approximation comes in the specification of the model itself. But once you have that model, we compute exactly the probability that that y equals 1 or y equals 0. Right? And that was done, remember, just with Bayes' rule. You just all did it on your homework. But it will turn out actually that in general, this is great. In general, there's no way to actually do exact inference for a lot of cases. I won't bother sort of saying it too much here, but we'll see actually a case later on, which I'll show you kind of in an extension of the change point detection setting, where basically you cannot solve inference exactly. And actually, even more than that, almost whenever you have continuous parameters, except in very rare cases, kind of naive Bayes only work because we had a discrete thing to compute distribution over. Whenever you have continuous parameters, you almost always can't do inference exactly. So because of that, it's more common in practice to see approximate methods used for inference. So rather than trying to compute the actual distribution, which may be intractably hard, people tend to find different ways of approximating it. And there are essentially two approximate approaches. One are called variational methods, which is a fancy word, but all it really means is that we try to approximate the distribution with simpler distributions by optimizing some characteristic of the simpler distributions. We're not going to talk about that one at all. That one actually is a little bit complicated and I think doesn't really fit well into, a one quick kind of overview lecture. The one we are going to talk about, though, are sampling-based methods. And this is actually really kind of the workhorse of probabilistic methods, or at least of approximate probabilistic methods, are these sampling-based approaches. And the idea here is that we're not going to actually try to exactly describe the distribution of the unobserved values given the observed values. What we're going to do instead is just draw samples from this distribution. And really this is, from samples like that, if the samples are really from the distribution, you actually can answer any question you want about the distribution. For example, if it's just naive Bayes and you can draw a lot of samples about what y is, well, you can just estimate, the class is just you can estimate the probability of the class just by how many samples you see equal to 1, how many samples you see equal to 0. When your unobserved variables, though, are much higher dimensional, sometimes it can be hard to represent the whole distribution over them, while representing drawing samples from them is much easier. Okay, but before I get into that, though, let me actually first mention some notions of exact inference. So, and let me use the example. I guess I could use naive Bayes too, but I'll use the example of the mixture of Gaussians. So, the mixture of Gaussians model, remember, was saying that we first sample z from a categorical distribution, and then we compute, or then we sample x given z equals little z from a normal distribution with mean mu z and covariance sigma z. And if you remember, the expectation step for the EM algorithm actually involved exactly computing an inference question. So what this model looks like is that you have z there that's not observed. All you observe here is x, so this thing is observed. It's hard to draw the shaded thing in the with one color pen. And what we want to compute, if you remember, for the E step, is we want to compute the probability of different possible values of z given some value of x. Okay. And so this is an inference task because we are inferring something about the unobserved variables given the observed variables here. Now, the formula for this was this is just equal to. We just use Bayes' rule here. So the probability of little x given z. Sorry, I should say the probability z equals z there equals the probability of little x given z times the probability of z over the sum over all z prime, the probability of little x given z prime, probability of z prime. Okay, and I have all these terms. These terms are all sort of defined exactly in my graphical model there, or equivalently in the generative model. Right, because this term here is just this p of the categorical probability, and this term here is just this thing, then the normal distribution. Okay, so what I want to point out here is that actually inference in the Gaussian mixture model is something that we actually already solved, and we solved it with a simple application of Bayes' rule. But again, the problem here is that this strategy doesn't always work. And when you observe when there's a lot of hidden variables and they have some structure between them, it's less clear how you apply Bayes' rule. Or maybe the things that you're summing over here is, I guess this would be the same case, but possibly the things you're summing over here, the set of all hidden variables is just too big to sum over. There's too many things to compute there, or they're infinite, they're continuous. And then the question is, what do you do? How do you actually model solve this inference task? So to introduce sample-based inference, I'm going to first discuss one really simple thing you can do, which is called rejection sampling. Okay? So the idea here is I already know how to generate samples from that entire distribution. And the only question is, I want to know what the distribution is given this has some value. This last variable here has some value. Right? So, for naive Bayes, I want to know the distribution of z given all my features. In this chain here, I want to estimate what's the distribution of these guys here given my feature, or given the observation of x4. So one thing we can do is just generate samples from the data as if we hadn't observed that variable, right? So I know my generative process. I'm assuming that I know all the parameters here of these models always. I can just draw samples of this whole thing, right? I first sample x1, I sample x2, I sample x3, I sample x4. Okay? But then after I've done that, I check, is my value I generated of x4 equal to the real x4 that I've observed, or is it not? And if it's not, I just throw it away. So that's I reject that sample. Otherwise, I keep it. And it's not too hard to see that, if I just follow this process, then all the examples I keep will be an estimate, or at least will be samples from the distribution of this whole thing given the observed value of x4, right? Because all I'm doing is I'm just throwing out the samples that are inconsistent with that observation, and that gives me, therefore, from that, the posterior distribution given that observation. That's what it really is. Okay? The problem here, of course, is that, as our models get more complex, the probability of observing any actual data goes to 0. So imagine this for one of these document topic models. What you have to do to use this approach, what you have to do is you would have to basically generate random documents from random words until you happen to generate the exact document you're looking at, and then that would tell you something about the topics that you've come up with. And if you generate words randomly, the chance of generating exactly the document you've seen is probably pretty low. You're going to be doing that a whole long time. So this is a simple model, but it doesn't really get you much. What people actually do, the actual sampling-based method that they use, belongs to a class of algorithms called Markov chain Monte Carlo methods, or MCMC methods. Now, I'm not going to describe this in any detail here, because they actually do take a little bit of time to describe, and it's a fairly complex kind of process by which you go about generating or deriving some of these algorithms. But the basic idea is that these are the only key points I want to take away here, because we'll see people use we'll see some uses of MCMC methods in the code examples, and so this is going to be the the workhorse really of probabilistic models. But the whole idea of all these things, and there's a bunch of different variants, and actually a lot of the samplers, the code out there will use sort of very fancy variants here. But what they all are is they're all iterative methods, right? So rather than sort of just doing one forward sampling and rejecting or not, maybe I start with some initial guesses of everything, of my hidden variables, and then I kind of iteratively update these guesses based upon the observed data. Right? So for instance, one of the more classic methods for Markov chain Monte Carlo is a method called Gibbs sampling, where you basically repeatedly resample each of your hidden variables by conditioning on both the things you observe and everything else, all the other hidden variables in your data. So I'm going to resample some hidden variable zi. Again, the z is referred typically to my unobserved variables. The x is referred to my observed variables. So in this case, as confusing as this is, these would be sort of the z variables here, and this would be the x variable. But what I do is I iteratively sort of fix all but one, and then resample this given the setting of all the others. And this is actually not obvious, but it turns out that for really any probabilistic model, it's possible to do something like this, something very close to this, that is sampled as one variable given all the others, even if it's hard to sample sort of all the variables given the observed data. So that's not actually maybe that obvious, but this process of sampling one, given everything else being fixed, tends to be usually pretty easy. Yeah, question?
For this rejection sampling, where does the distribution that you're sampling come from?
The question was, for this rejection sampling, where did the distribution come from that you sampled from? That's just the generative model, right? So the generative model, you have a model of this thing. So the inference problem always assumes you know the model. So I've already estimated all the parameters of my model. We'll talk in a second about how oftentimes it's actually pretty easy. You sort of assume. Anyway, we'll get to that in a second in Bayesian modeling. But assume you know all your parameters. I know all the fees of my distribution. I have a model that describes this. It's just this model here.
So if you have the model, what are you trying to find out?
So the question is, if you have the model, what are you trying to find out? What I'm trying to find out is, I have the model, but I want to know what is like with naive Bayes, right? With naive Bayes, after you fit it, I have the model. But what I want to know is, given some observations, given that I observe some variables in this model, what's the probability over the remaining variables? So for naive Bayes, for example, given that I've observed some set of features, what's the probability of my different classes? For the Gaussian mixture model, given that I've observed my data point, what is the probability of different cluster assignments? That's the inference problem, is that given some things, estimate the probability over others. Which again is sort of the whole idea of data analysis in some point, right? In some sense, right? It's that given some observations, I want to make inferences about what's the likely value for other random variables. So here's our model, right? This is our model. We know the model. We've also been given the additional information that x4 is equal to 0. And I want to know if that's the case, how does that sort of change my distribution over my other variables here? Or if, in the case of naive Bayes, if I'm given some features, how does that change my distribution over the y's, over the possible classes? Now, rejection sampling is not the right thing to do. You shouldn't do this. What you should do instead are these sort of iterative processes. And the most common ones are Gibbs sampling, or a little bit more complex method called Metropolis or Metropolis-Hastings for another edition. And this basically is something similar. It also, and this is actually a certain form of Metropolis, but basically it samples not even just from this exact thing, but from some sort of surrogate distribution Q, it's called, and then has some rule for either accepting or rejecting that update. And again, the details there really are not important for the purposes of this class. All I'm trying to convey here is that there exist very powerful iterative methods for approximately sampling from the posterior distribution over some variables given others. And the nice thing, as with a lot of things that are useful in practice, is that libraries for this kind of analysis are well established, and you can just kind of use them without worrying too much about how these things work internally. Okay, so before I go on, are there any more questions? Okay, so the last thing I want to talk about before I dive into an example, and maybe I should have gone to the example even first, but I have to describe it in some detail first. The last thing I want to describe before diving into sort of what this looks like in code is I want to talk about the idea of Bayesian modeling. So throughout this, and this is now kind of stepping back a second, because there's a sort of an important distinction here that I want to emphasize. So throughout this class, we've sort of had two different sets of things we've thought about when it came to modeling data. Right, these were, on the one hand, you had random variables. These were sort of the things that had probabilities, the things that you take expectations over, or the things you try to model their distribution. And then you also had what we called parameters. Right? These were sort of single numbers that you would optimize to, fit a distribution or to minimize some loss function, right? So roughly speaking, variables are the things we take expectations over or we sample from, and parameters are the things we optimize. We optimize parameters to fit some data. And the canonical example of this is maximum likelihood, right? Where we have some parameters that govern our model. We have a probabilistic model, and we have some observations, and we we choose our parameters to maximize the probability of observing our data under that distribution, right? That was the idea. That was sort of the thing that tied together, loss functions and probabilistic models. The idea is that a lot of things can be viewed kind of in this framework. So this is our kind of standard way of fitting data. Now, what Bayesian, and this, by the way, though we didn't ever frame it here, this is something known as frequentist modeling, which won't define what that means actually. I'll just contrast it to a different point of view, which is called Bayesian modeling. Now, the key idea here in Bayesian statistics is that instead of trying to find kind of a single estimate of our parameters, so given this data, I'm going to estimate what the mean of this data is. Instead, I'm going to treat all my parameters themselves as random variables. Okay, and really, there isn't too much more that you can convey, in this length of time about Bayesian modeling, but that really is the key, is that instead of trying to estimate parameters exactly, we want to think about trying to think of parameters themselves as random variables. So, and again, I use a different notation here. So instead of using the notation P of xi, I guess, parameterized by theta, that means a distribution that's specified by theta. I'll instead use the notation P of xi given theta. And this is meant to emphasize here that theta itself is a random variable. And so, our distribution might be conditioned on the value of theta. All right, so in order for this to make sense, though, in order for us to make sense of having parameters be random variables, so my least squares coefficients are themselves a random variable. Right? That seems hard to kind of make too much sense of. But the idea to do this is that we need to think about having some probability over the random variables themselves. And this is called a prior distribution. So in Bayesian statistics, we think of parameters as themselves being random variables. And they, therefore, need to have some prior distribution over them. To have some, nominal distribution over what those values should take on in the absence of any actual data. And in fact, because these distributions themselves have parameters, it'll often be written like this. Alpha, where alpha here are called hyperparameters. They are sort of the things that govern they are, meta parameters that now are really parameters. They aren't variables themselves. You can, of course, keep doing this to infinity, right? You can keep having alphas now be random variables, and it's one more thing. But really, actually, in Bayesian statistics, usually just these things, unlike what we did before, we will actually not optimize those parameters. We'll just fix those parameters at some nominal value, and we'll leave it at that. And the entire goal in some Bayesian statistics is the following. What we want to do is, we're given some data, which I'll call x. And we assume that we know the distribution of P of each xi given theta. And our goal is to find what's the posterior distribution over theta given our data. Okay, so this is the key question. Without any data, we have some prior over our parameters. In other words, we sort of think our parameters are going to be in some region. And then we observe some data, and we want to know. We're not going to try to find like a single set of parameters that sort of explain that data. Instead, what we're going to do is we're going to say, I want to know how does observing that data change my posterior distribution over my parameters. Right, so what's the posterior distribution here over my parameters theta? And in general, we can just use Bayes' rule to do this, right? So this is the probability of the data given the parameters times the probability of the parameters. We have both these things, right? This is our prior here. This here is our data observation. And then we would then compute, we then sort of divide this by, well, the probability of the data itself, but in this case, that would involve an integral now, because theta is continuous, of p x theta prime, p theta prime, and d theta prime. Okay. We don't deal with integrals too much in this course, but occasionally we have to deal with them, because essentially this is just the probability of x here. I'm integrating out over theta, or marginalizing out over theta, but because theta is a continuous random variable, typically like our mean parameter of a Gaussian distribution, we have to have an integral here. Okay? And this is the goal of Bayesian statistics. It is find the posterior distribution over our parameters given the data. So let me now take an example of this, which I will actually use as the example that we have in code as well. Okay, so this is now going to actually be a Bayesian change point detection model. Okay, so as before, we have x. You can think. I'll bring back my figure here. Where did I have that? Yeah. Okay, so as before, we have a bunch of points. We have a bunch of x points and y points, right? Where x here is sampled but uniform between 0 and 1, and then y sort of has one of two different distributions. So if x is less than some threshold t, then we're sampling from one mean. If it's greater than that, we're sampling from another mean. And we use the same variance here, no matter what. The difference in the Bayesian setting, though, is that unlike the sort of setting we described before, which was really what could be called a frequentist setting, in the Bayesian setting, all these things, so the means and the variance and the change point here, are themselves also random variables. Okay, so they also have their own priors, and so t is a uniform distribution between 0 and 1, right? Our change point is uniform, say, between 0 and 1. If we had some reason to believe that maybe it's more likely to be in the center, we could encode that in our prior over our change point that would actually help us kind of determine where in that range it was. Our means there are actually themselves normally distributed with mean 0 and some arbitrary covariance. Sigma squared is actually what's, in this case, comes from an inverse gamma distribution. Don't worry about that at all. It turns out there's something nice about using an inverse gamma for the variance of a normal distribution. It's always, it's a distribution that's always positive and has some nice properties there. But the basic idea, and so the point is that all those other things, right, all these terms in the model, the variance, the two means, those are also all random variables that have their own prior distribution. And so our goal of this model is going to be to compute the probability, or maybe not compute the analytic probability, but somehow describe the probability over, given some data, what is our likely estimates, sorry, I shouldn't even worry about the estimate. What is the distribution over possible values of our parameters, i.e. t, mu1, mu2, and sigma squared. Okay? I should say given our data. Okay? So what this is saying is, if I observe a bunch of data, if I observe this data, what is the distribution over possible values of my parameters? Right? I should have a poll question on this, but maybe before I get to that, let me actually say what this looks like in code, and I'll return to the poll in a second, actually. Because I think this can become much more concrete if you think about actually writing these things down. So I'll jump back to the poll in a second. It's actually kind of doesn't even relate to this. It's a simple question about that model, but we'll go back to it in a second. What I want to talk about before I get there, though, is this notion of probabilistic programming. So this looks pretty complicated, right? I mean, it seems like kind of a complicated model, but at the same time, you know, if I were to give you methods of sampling from each of those distributions there, you could just do that, right? You could sort of sample from, you know, a uniform distribution to get t, sample from normals to get mu1 and mu2, sample from an inverse gamma, if you look up in Wikipedia how to do that, to get sigma squared. Then for a bunch of times, you know, you sample x uniformly and you sample y according to that this thing. I should say that like what you actually do is you sample the top things once and you sample these many times. So x and y are sampled many times, kind of according to the picture I showed. So that's kind of complicated to do, right? And especially what would take me even a while to do is figure out a way to compute this distribution now, or you know, generate samples from this thing, given some observations. How on earth would you actually, you know, compute samples over your posterior distribution there? Fortunately, though, the work of this has all been done for you. What this means is, and this is actually also a very powerful point, which would be the other main takeaway you can really get from this lecture. In recent years, there's been a huge effort to kind of automate the process of doing Bayesian inference, all right, of doing probabilistic inference, where you specify a model, specify some observed data, and then let the system tell you, how to draw samples from your posterior. This is actually not unlike the work that's been done in deep learning, right? Where now we have tools like TensorFlow and MXNet and these kind of things that make it very easy just to specify, the forward pass of a deep neural network, and to automatically get ways of computing the gradients and updating it, training this to fit some data. Similarly, in probabilistic programming, we've actually there's a lot of tools that let you specify the generative model of some process and kind of automatically generate from that a method of sampling, from the appropriate distributions of this data. The one that we're going to use actually in this class, and you'll use it on the homework if you choose to do that question, is the PyMC2 framework. There is a newer version of PyMC called PyMC3. I was thinking I'd want to use this because it's a more modern one. I actually chose not to because there are some oddities here that make it actually kind of much less nice to use. So I'm actually going to keep using PyMC2. This one's a little bit trickier, and it uses also Theano behind it, which is now a deprecated or non-supported numerical integration library. It's actually sort of a predecessor to, sorry, not numerical integration, numerical differentiation library, a predecessor to TensorFlow and these kind of things. But basically, this one is kind of harder to use, and it's slower for simple things too, because it tries to compile everything on the back end. So we're going to use PyMC2, but I should emphasize there are a lot of similar tools out there. And things, if you've heard of libraries like Stan or Edward or Pyro or these kind of things, these are all in the same class of what are called probabilistic programming languages. And these are, I should say, only the ones that run in Python or something similar to it, or R or something like this. There are this notion of probabilistic programming actually goes well back before this. Long before those languages came out, but those are kind of some of the current ones that are popular these days. Okay, so let me just jump right in and look at what this actually looks like. So actually maybe I'll write my model again. So my model was, T was uniform between 0 and 1. Mu1 and mu2 were normal, and actually I might just give them a fixed distribution there. Mu1 and mu2 were normal, say with mean 0 and covariance, or variance rather. What did I use? I think I used 0. Variance 10 or something like that, so they're can be spread out. I said sigma squared was normal, was inverse gamma with, I had like terms alpha and beta, and I actually forget what those are, so I'll just leave them as that. And then with this, each xi was uniform, 0, 1, and yi was equal to normal with mu1 and sigma squared if x less than or equal to t, xi less than or equal to t, and normal with mean mu2 and sigma squared if xi greater than t. Okay, so this is our sort of generative model, and I'm going to show you now the code that generates this. So the one thing that I'm doing there is a little different here is that PyMC2 in normal distributions actually does not parameterize them by their variance. It uses the inverse of the variance. So the second term in the normal distribution is actually 1 over the variance, not the variance itself. So just know that. But essentially, I say T is a uniform distribution. You have to name your variables, so it's the name of the variable is T with mean 1. Mu2 is normal. It's called mu1 and mu2 are both normal with 0 mean and what comes to variance of 10. Tau is actually going to be the inverse of sigma squared. And so whereas sigma squared is an inverse gamma, this is just a gamma variable. That actually is not really important. The only importance there is that those are typically what are used for the distribution over variances in Gaussian distributions. That's the only thing you really need to know. So I specify sort of my parameters there. And then here I sample x uniformly. I actually have to sample n of them because I have a bunch of those samples, but they're all uniform between their 1. And then y is normal with mean equal to this term, xi less than 2, so that's going to be 1 if it's less than that, otherwise it's going to be 0, times mu1, plus this term is going to be 1 if it's greater than t, times mu2, so that's how I select my mean there. And then inverse of the variance is equal to. Okay, so this is now all I actually do with my model. And then if I want to do something like sample from this distribution, I can call MCMC, pass my list of variables into it, and then generate 100 samples from that distribution. Now this is just generating pure samples, right? I'm not actually observing anything here. I'm just following the generative model story and generating samples of my data. So that, if I just run exactly this, it'll look like this. Okay, it'll look like what I'm doing here is I'm sampling t, right? Uniform between 0 and 1, and I'm sampling all my means and variances differently. So what I have here is, I have basically different examples of 100 points drawn where I randomly pick some threshold. I randomly pick some variance, and I randomly pick 2 means. Okay? And each one, of course, has different threshold, a different variance, all this kind of stuff. So that's sort of the samples you see there. Okay, now the last thing I'll say before we go back to our poll question is the more interesting question in some sense is if I observe some data, how can I infer something about where the change point was here? And then what the 2 means are and what the variance is, right? It's great that I can do this, but this is sort of a simple question, right? This is just sort of saying, okay, I have this process. I just, I first sample those up there. I then sample those. And while this is nice that you can, basically have random samplers that work for you, where you don't have to write, these all randomly sampled from the appropriate distribution, isn't really that useful because it's just sampling from this posterior kind of, or sampling from the prior kind of naively. What's nice, which I'll show you in a second, is how you actually incorporate observed data into this inference procedure. There's a question first?
For PMs and PMC, does it resample the parameters or always just the
It will sample all these things. So you give it a bunch of things, right? A bunch of essentially random, you should think of all these all as random variables, and it will generate 100 different samples of these random variables. But importantly, this is actually itself n different random variables. So it samples, all 4 plus 2 times n random variables, according to this generative process here. But what's important, of course, is the ability you can actually incorporate observations here. So instead of sort of sampling randomly, the real question you actually care about is that, what if I have data like this? I'm given some x and y's, and I want to fit this model to it. In other words, I want to sample, what's my distribution over possible means, over possible variances, over possible change points, given this kind of data, right? And the nice thing about these probabilistic programming libraries, including PyMC, is that this is very easy to do. So everything remains exactly the same. The only difference is when you define your random variables, the x and the y's in this case, you set them to be observed equals true, and you set their value. Okay, so now they're actually constrained not to be whatever they want, but they actually take on the certain values that you observe. Right? And now when I run this, what I'm actually sampling from is the posterior probabilities over my other variables, right? Over the t, mu1, mu2, and sigma squared, given these observations. And that, by the way, I would not be able to write the, I could after a while, but it would take me certainly a lot of work to write a, Markov chain Monte Carlo sampler for this probabilistic model here. It would be a real pain. I wouldn't want to do that. So the nice thing about these methods is that it lets you kind of do this all automatically. And what they generate is something like this. So they generate samples. There's actually a parameter here called burn2, which is the number of samples you sort of run it first before, and then you throw away. Because the first few samples, actually, in these iterative methods, will not actually be a very good approximation to the true posterior distribution. They're kind of, getting to the right place, and then you start collecting a lot of samples from hopefully the correct distribution. So what I want to do now is, so I sampled, 10,000 samples, but I threw away the first 100. Those are, by the way, very sort of ad hoc things. You have to kind of play with them until it seems like your distribution's converged, and then you keep going from there. But what I'm going to do here is I'm going to actually now plot. I'm going to take all my 9,900 samples left. I'm going to plot histograms over these things. So this is going to be, in the sense, our representation for the posterior over the remaining variables. And this is what we get here. So t, which is our threshold parameter, is it's sort of almost like a uniform, not quite, but basically like a uniform distribution between 0.44 and 5. And the reason for this is that if you look at our data, there's no data. Clearly there's, clearly kind of sometimes the change point is right here, right? So this is, it should find t right kind of there. But there's actually no points between 5 and about 0.44. So t is uniform in that range, right? There's no way to prefer one change point there over another, because they have no way of knowing where in that range would be, so our range is uniform there. Similarly, we're trying to estimate the means, and because there's some randomness here, right? Because these are ultimately of Gaussian samples, there's some variance in basically how big our means could be. But I will tell you, in fact, that the true mean of the higher one is 1, and the true mean of the lower one is -1. And these distributions that we sample from are pretty nicely peaked around those two values, right? Similarly, the variance, I think, is 1 over. So the variance is 0.25. And this is 1 over the variance, so actually it's the true value is 4, but it's a pretty good estimate, a pretty good distribution over that. This is just due to the errors. There's sort of these are random sampling. Sometimes you get it wrong, sometimes you get it right. Now, again, you can use this to say, okay, we're going to go ahead and compute, estimates now of my, threshold parameter. I think it's like the average of these things. Maybe I think tau is the average of those things, or the mode maybe, or whatever. But really, in the true Bayesian sense, you actually would just want to look at these distributions, right? And in fact, this is even too much because they're also all correlated. So you want to look at or think about the true high-dimensional correlation of all these things. This is our answer to a certain extent in the Bayesian setting, right? Our Bayesian setting says we don't actually want to come up with point estimates for these variables. What we want to do is we want to capture their distribution. And this method has let us capture that distribution by essentially providing a way to draw samples from that distribution. And that's what these libraries enable. Okay, so I have one sort of poll question here I'll put up, which is to ask, what's the model, what's the picture model for this generative story, or the Bayesian network, I guess I'll say it, but for this generative story. So remember, in a Bayesian network, you specify the distribution of each element given its parents. That means that each distribution is specified in terms of the variables it directly depends on. And so the question is, what would be the graphical model structure of this generative process? And I have one more slide to show as well if we finish this poll early. Okay. So I think we'll actually not cover the next point. We'll spend some time talking about this. All right. So pretty even split. All right. And I'll just say it. So sadly, the answer is actually also A, which is the lowest of the slightly even ones. So I think I should spend some time talking about whether this is true. Okay, so the notation of a Bayesian network, remember, means that each variable's distribution is specified in terms of its parents in the network. In this network, only y depends on anything else in the network. Right? So T is uniform 0, 1. That has no other parameters. U1 and U2 are sampled 0, and then this nu, but nu is not a random variable. It's actually a parameter, a hyperparameter, so we don't include it as a random variable. So it depends on nothing. Sigma squared is inverse gamma. X is uniform. None of those things actually depend on any other elements of the network. Right? So they are just sampled all independently from each other. You flip sort of independent coins each time. Now, the y variable, though, depends on all of them, right? Because the y variable, depending on the value of x, it compares x and t together, so it depends on both x and t. And then depending on the setting, it has the mean mu1 sigma squared and mu2 sigma squared. So this is actually the correct graphical model that describes this procedure here. And the idea is that this says that y, because they are all parents of this, that y's distribution is a function of all its parents. Whereas these other ones, say x has the parent of these sons, x is independent of these variables, or at least marginally dependent of these variables. And so this is not captured, these effects are not captured by either of these two models, and this structure is just sort of, there's no logic to a structure like this, right? There's no way in which mu1, mu2, or sigma depend on t. They're always independent. Okay, so again, this includes sort of our one-off topics for the class. We're going to switch gears a little bit next week and talk about, at a higher level, debugging data science and how you actually go about solving problems data science when your first methods don't really work. The first things you try don't really work. So it's actually a very useful lecture, especially for your projects next week. And then on Wednesday, we're going to do kind of an example walkthrough of a data science problem. So that's what's going to be happening next week. So this is sort of the end of our technical content in some sense.